Что у нас здесь? Okay, welcome everyone to our last in this year meeting. So our speaker is Boris Kruglikov from Tromsø. Boris, you are welcome, and let us begin.
Okay, very good. So let me share screen. Can you see the screen?
Yes.
Yes, in big mode, and just recheck.
Well, just a minute. I want to switch off microphones. Okay, and now we begin.
And you can see my slides running,
Yes,
right?
yes, but maybe they are not full screen.
Okay, let's make some cool full screen.
Yes, yes.
Okay.
Now it's perfect. Yes.
Okay, thank you very much. It's a pleasure to talk on the seminar as always. So I will talk on joint work with Evgeny Ferapontov. It's about GL2 geometry and application to dispersional integrable hierarchies, or rather relation. So GL2 geometry or paraconformal geometry on n-dimensional manifold is defined by a field of rational normal curves in the projectivized cotangent bundle. So here we take, let me see, maybe I can flashlight it. Right, so okay, so here we have at every point of cotangent bundle, we take projectivization, and then we take a rational normal curve. So that's will be projective space of dimension n-1, and the curve will be of degree n-1. And that's kind of generic algebraic curve here. So it means that in some coordinates is given, this curve is given by the formula lambda goes to 1, lambda square, and so forth in the projective space. And since it goes from point to point, it means that we have coframe on a manifold M such that this curve is given as follows. So I write it actually in cotangent space, right? This is a curve of cotangent space, but we have to projectivize. In particular, this choice of the first coefficient to be 1, it's convenient parameterization for projective thing. Okay, but then we can do the following transformations. As the parameter lambda is projective, and that's the Möbius transformation for lambda. And the form omega is, well, conformal, so we can scale it because we don't see it, right? So the curve is in projective space. So R is conformal multiple, and this multiple is needed just because when we do this transformation, there appear denominator here, and that's clearing denominator. We will later not do it, not mention it, but just will clear denominator every time we need. So all A, B, C, and so forth are functions. Conventionally, GL2 geometry can be also defined as a field of rational normal curves in projectivized tangent bundle, PTM, not without star. And both pictures are projectively dual, because if you take equation omega lambda equal to 0, right, so that's covector depending on lambda, then for each lambda we have a hyperplane. So we have one-dimensional family of hyperplane. And due to non-degeneracy of the curves, it's actually these osculate a dual rational normal curve. So having a curve, we can take as first osculating, it will be surface. We can take second osculating, it will be three-dimensional thing, and we can come to codimension 1. That's duality. Okay, so GL2, where do GL2 geometry arise? In Poisson geometry, namely as compatible bivectors of Kronecker type on odd-dimensional manifolds. And these were identified by Gelfand and Zakharevich as Veronese webs in the theory of bihamiltonian integrable systems. In exotic holonomy, in dimension 4, there exists torsion-free affine connections whose holonomy group is a irreducible representation of GL2, right? So GL2 has four-dimensional representation, irreducible, unique. And this gives basically parallel GL2 structures. Because if you take GL2 representation in 4-dimension, you take the induced action on projectivization on P3, and you take the minimal orbit. That's rational normal curve. And it was observed by Bryant that there exist unique torsion-free connections of this kind, preserving the structures, and this was a first example of exceptional holonomy not appearing in Berger list. In algebraic geometry, so if we consider a modular space of rational curves in compact complex surface and fix the normal bundle to be ON, then the modular curve of this has dimension n+1. And it naturally carries GL2 structures. For n equal to, they were studied by Cartan and Hitchin, for n equal to 3 by Bryant, and in general case by Dunajski, Todd, and then by Krinsky. In ODE theory, so if you consider ODE of order n scalar, with vanishing Wünschmann or Dubrov-Vilchinsky invariance, then its local solution space is canonical end of this GL2 structure. And it's not arbitrary GL2 structure, we'll talk about later, so-called involutive. And this class of ODEs with vanishing Wünschmann invariance also appear in a different context, because by the result of Chap-Dubrov-Te, it satisfies the called C property of Cartan. So every differential invariant becomes integral for this ODE. And therefore, if the ODE is sufficiently generic, there's enough first integrals, and the differential, the ODE can be integrated without integration. Algebraically, can be integrated by algebraic means. In Grossman geometry, so if we consider submanifolds in Grossmanian, they inherit naturally, well, from sacred structure in Grossmanian, they inherit what is called generalized conformal structure. In the particular case of fourfold in Grossmanian 3.5, so Grossmanian 3.5 has dimension 6, and this is codimension 2 submanifolds. Then this generalized conformal structure becomes actually GL2. And in the work joined with Dubrov, Ferapontov, and Novikov, we encoded integrability of the corresponding system. So once again, so this is codimension 2 submanifold in here. In Grossmanian, usually this fiber of the first jet over the zero jet. So it encodes a PDE system of first order with 2 independent and 3 dependent variables. So this is 3 and 5 minus 3 is 2. And in a similar way, if you consider Lagrangian Grossmanian 3.6, which has dimension 6, and consider hypersurface, which has dimension 5, this corresponds, that's coordinate-free way to encode second-order PDEs. And such hypersurfaces inherit from Lagrangian Grossmanian GL2 structure, and integrability of this PDE can be encoded in properties of this GL2 structure. Okay, so what I'm talking about today is the following. So we first of all establish that dispersionless integrable hierarchies of PDEs in 3 dimensions provide GL2 geometry on the solutions. So that's a bit different which we had in previously, because here actually it was GL2 structure on equations. Okay, so these things encode actual equations. But here we talk about GL2 structure induced on every solution of the, well, PDE or hierarchy. Okay, and in fact, this association GL2 structure is very simple. It's just characteristic variety, and I will show it in examples how to see it. And we just truncate hierarchy, get fine dimensional manifold, and then get the GL2 structure. The structure which arise, they are special kind. They are involutive GL2 structures, and this was popular in the literature. So in particular, we obtained what I mentioned before, torsion-free GL2 structures on Bryant and totally geodesic GL2 structures of Krinsky. And this totally geodesic GL2 structures equivalent set is that it possess compatible affine connection. Well, torsion may exist, and two-parametric family of totally geodesic alpha manifolds. So this actually in dimension 3 becomes precisely Cartan characterization for Einstein-Weil geometry. So that's a generalization. And in previous work with Evgeny Ferapontov, we established that in Einstein-Weil geometry is encoding integrability of 3D dispersionless equations. So we hope, like this gives a hope to see integrability, well, in bigger dimensions. Okay, so before I go to explanation what means involutive and all other stuff, let me show you examples. So here's Veronese web hierarchy. So you can, the Veronese web equation is a PD of this kind. C1, C2, C3 are constants, and you can take ijk to be 1 to 3. And the hierarchy consists if taking very similar equations, right, with more constants. And now you allow function u to depend not only on x1, x2, x3, but also on x4, x5, and so forth. And that's partial derivatives here. And the word hierarchy means that we obtain very many equations, well, finitely many if we are truncate, or infinitely many if we allow this to be infinity, and all of them are compatible. Okay, but we say that it's hierarchy of 3D equation because actually at the bottom of this embedded sequence is just one equation. This one, well, for ijk equal to 3. Now we go to characteristic variety, and I recall what it is. So actually, I will not tell it in general because the equations are actually quasi-linear. In general, you have to also linearize the system, but for quasi-linear, you basically don't need to do it. You just look to top derivatives, right? And that's derivation by ij, and you do Fourier transform. So basically, you freeze all over all the derivatives. And then you get linear equation, well, linear in those variables, right? And you do Fourier transform, which changes differentiations to multiplication, and this multiplication by momenta, pi. So differentiation del I go to pi, del j go to pj. Okay, so that's so simple. Okay, so we get this characteristic variety of the system. And you see it's some huge collection of quadrics. Well, some of them are linearly dependent. And it's actually specify a rational normal curve in PT star M, where M is actually Rn, where this coordinate goes x1, x2, and so forth up to xn. Okay, and pi coordinate on the cotangent bundle. So to see that it's actually a rational normal curve, it's possible to note that whenever we take such substitution for pi, then we get identity in here. Okay, and you see it's actually contains arbitrary parameter lambda. And if I put, this standard form for covector pi dxi, right, that's omega lambda, then I have this expression. Of course, it's not polynomial in lambda. You have to do what was said before. You have to clear denominator, and then you will have actually a polynomial of degree n minus 1. Okay, so that's actually a rational normal curve. And there's a bit more because that system is integrable. That's actually hierarchy. And in which sense it's integrable? It's integral in the sense of Lax representation. So it's not Lax pair, it's more, right? So if, of course, if it's just three-dimensional system, which is at the bottom, that it will be Lax pair. But when we consider hierarchy, it will be more. It will be for each j between starting from 2 to n, we'll get such a vector field. And so we get in the extended space of x's and lambda, we'll get a distribution of codimension 2. Well, so its dimension is n minus 1. And if you write Frobenius condition for this distribution, it's satisfied precisely modulo the system. It's actually equivalent. Okay, that's integrability. Okay. Now, another example is DKP hierarchy. So the DKP hierarchy has this form. And again, if you take this smaller, so that's, well, you can truncate it. You can say that J is less or equal than N, and then you get a finite dimensional PDE system. It is compatible. And if it's smallest possible range of indices, namely I equal to 1, J equal to 2, then we get three-dimensional equation. So x1 will be x, x2 will be y, x3 will be t, and then we get known DKP equation. Okay, so we again do the same trick. We take the heuristic variety for this system. Here it is. We see it's family of quadrics. Again, it defines rational normal curve. And it's parameterized as follows. So we can put the first coordinate 1, well, because it's projective variety as we see it. And then we actually can successively find all pi plus 1 through the lower pi and pi minus 1 and so forth. Okay, so we can unite all of this into omega lambda again. And there's dispersionless representations. The difference between this example and the previous example is that here in Veronese, there's no d by d lambda, so it's isospectral, while here there exists d by d lambda. And the final example is the universal hierarchy, so which is this system. Again, you see it's quasi-linear. Well, I restrict the range here. And when we take n equal to 3, right, as you see is j plus 1. So then with the same notations before, so we get this equation. So become more familiar. And yes, we take for hierarchy heuristic variety. So we get this resolution. We can, again, successively resolve all p in terms of previous ones. Or we can just like unite them and get this omega lambda. Okay, that's pi here. And the dispersionless representation is here, doesn't contain d by d lambda. So that's representation for this. Okay, so what is actually involutivity, or as Krinsky called alpha integrability? So for so we may just say it for manifolds. We don't need at this point actual equation. So if manifold M possesses GL2 structure, then at each point we have this equation: omega is covector depending on lambda, projective parameter. And so it has one parametric family of hypersurfaces in tangent space. They called alpha, well, hyperplanes in TXM. That's all called alpha hyperplanes. And hypersurface in M is called alpha manifold if at each point of this hypersurface the tangent space is alpha hyperplane. Okay, so that's not Frobenius integrability, right? Because that's not a distribution. At every point we have one-dimensional family of hyperplanes. Now, GL2 structure is called involutive alpha integrable if for every alpha hyperplane we can find alpha manifold which is tangent to it. Okay, so what we do then? So here's our manifold. Well, you may ignore U for a moment. So what we do, so that's n-dimensional manifold, right? And so we consider bundle over it, and that's this P1 bundle of all possible lambda. Okay, because at each point we have, for each lambda, we have alpha plane. Now we resolve it, right? So it's here actually, there's no this ambiguity. So we can think that we have one hyperplane in a lifted tangent plane to this point. Okay, or equivalently, we can just take pre-image and we will have hyperplane in here if we add also d by d lambda vertical for this. But in fact, actually we can lift those hyperplanes to here. Okay, and moreover, those if it is alpha integrable, then those alpha manifolds can be lifted in here. So here it becomes foliation because it will pass through every alpha plane. And so we can consider local quotient. Okay, there is the co-dimensional foliation is 2. When we do local quotient, we get something two-dimensional. And that's what's usually called twister. So that's running here and here. That's called twister correspondence. Okay, now we can think due to previous story that actually this happens on every solution of hierarchy. So every solution is n-dimensional manifold. So I mark the solution U. So we have this. Then we have correspondence space above our solution. And then we can quotient and go to twister space. Okay. So now there's, yeah, and let me actually go back for one of the examples. So for example, for DKP, okay, so that's actually this distribution on this correspondence space, M hat of dimension n plus 1, right? You see d bit lambda appears in there, and on a solution, that's Frobenius integrable distribution, right? Therefore, we get local foliation, we can quotient, and we can go to twister space. So the invariant, the coordinates on twister space are precisely the integrals of this Frobenius integrable distribution on the correspondence space. Okay. Now, actually, there are a bunch of adapted affine connections for GL2 structures. So first of all, an affine connection is called compatible if it preserves the ideal of quadratic forms defining the rational normal curve. It's a standard fact in algebraic geometry that ideal of rational normal curve consists of quadrics. Okay, that's actually not a complete intersection, but it doesn't matter. We just take the span of all possible quadrics. Okay, and I write it in this form. And actually, in this form, it very much resembles what is Wild structure. So if you have a conformal structure on a manifold, then the Wild structure is a torsion-free connection which preserves the conformal class. Okay, and this is span, right? So that actually I don't write any multiple. Okay, that's precisely the same condition if you have only one quadric. Now, torsion-free is actually a pretty rigid condition, but we can start with it. So we may consider GL2 compatible connections, which are torsion-free. It turns out that such can exist only in 4 dimensions. That's a result of Bryant. So in higher dimension, such cannot exist. And even, but in 4 dimension, this notion is equivalent to involutivity. Okay, so basically, like for hierarchy, this becomes too much restrictive. Like you have 3D equations, you can take first truncated hierarchy, then such exists, but higher it will not. Okay, then the next interesting class is totally geodesic connections. And that's such a connections that they possess 2-parametric family of alpha manifolds. That's as for involutivity, but which additional are totally geodesic with respect to GL2 connection. Okay, and it was shown that this condition, it was shown by Krinsky, this condition implies Einstein-Weil property. So that if you take for this connection a rigid tensor, for general affine connection, it need not be symmetric, so we have to symmetrize it. And then this belongs to span, but not of G, but of G dual. So remember that this G is actually, so we have GL2 structure if a curve in projectivized cotangent bundle. Its ideal, therefore, consists of symmetric forms on they are element of second symmetric power of tangent bundle. Okay, so what we have to do, we have to dualize the picture. Consider the curve in tangent bundle, and then consider the corresponding ideal in cotangent bundle because this is in second symmetric power of cotangent bundle. Okay, but that's projectively dual. That's algebraic operation, easy to do. So in dimension 3, that's precisely Einstein-Well property. Okay, well, it turns out that this totally geodesic need not exist always. So in examples 1 and 3, which I showed, they exist, but in example 2 of DKP, such do not exist. Okay, so more generally, this exists for linear degenerate or isospectral hierarchies. Okay, then there's also a possibility to do normal connection. So we take GL2 compatible thing, but we impose a bit weaker condition. Namely, we impose condition on torsion of the connection. So torsion of the connection has to be trace free. So there's one index up, two indices down. If you take any contraction, it has to be 0. And then also, as it is a map 2 to 1, we can actually see how it maps alpha hyperplanes, and it has to preserve it. Okay, and totally geodesics are necessarily normal, but vice versa is not true. Okay, and then there's also a class of projective connections. So what we can do, we can take torsion-free connections possessing 2-parametric family of totally geodesic alpha manifolds. Okay, so we kind of unite this requirement and this requirement. However, we dropped this requirement of GL2 compatibility. This need not to be satisfied. So all these three can be satisfied only in dimension 4, but for higher not. And if we take this requirement and this requirement, such connection exists, but they are non-unique. And the difference between possible connections is just in projective transformation, right? So for such connection, geodesics are defined, but as unparameterized curves. That's called projective structure or projective connection. Okay, so normal and projective actually exist for all hierarchies. Okay, and we've been able to construct those for those examples which I indicated. Okay, so to summarize what was said so far, we have well, this involutive GL2 structure or paraconformal structures are important because they appear in many contexts. We can have them actually have many explicit examples because we can take any hierarchy, take explicit solution, and then produce by this, well, explicit involutive GL2 structure, which kind of was not possible before. But how to describe all of them, right? So examples are good, but how to describe all of them locally? Okay, so that's our first theorem. Parameterization of all involutive GL2 structures. So this is given as follows. So that's, remember that that's some pi dxi, and that's formula for pi. So in this formula, we use, of course, this projective parameter lambda, but also two functions u and v of n variables, and uj, that's partial derivative by j is similar for vj. Okay, that's partial derivatives. So we get that omega lambda depends on first jets of two functions. Okay, and these functions, well, in order to achieve involutivity, there's a system of PDEs imposed on those functions. And we call them E and F. And this bunch of E's and bunch of F's parameterized by 4 indices as well, ordered. Okay, so that's E. It's well, that's also A and B. They are not constants, but they are ratios on U and V. So B is actually A minus 1. And that's A minus A minus A, as you see. And there's some, well, quasi-linear expressions in U and V. Well, and very similar with I and J intersected, right? So you see that this, when I, J intersected with KL, and the same thing here. So if you interchange I and J and KLL, you get this. And you can see actually that this thing is fully total symmetric. And then you obtain F from E by interchanging U and V and A and B. Okay, and that's a cyclic summation. Okay. Now, that's formulation. Okay, let me give you an idea of the proof of this. So involutive GL2 structure possess alpha manifolds. Well, actually, there's always some amount of alpha manifolds, but we don't need many in order to start doing things. So we just need alpha. Well, in general, alpha manifolds parameterized by one function of one variable. So так, я прошу прощения, почему-то у меня вылетело все. И это было ужасно.
Теперь, слава богу, все на месте. Давайте обратно экран ваш.
Да, жутко прошу пардона. Окей. А где оно прервалось, я даже не знаю. Здесь или нет?
Да.
А я это успел сказать или я пропал уже?
Нет, по-моему, следующая страница.
Вот эту страницу мы дошли до конца.
Очень хорошо. Okay. I'm very, very sorry for interruption. Okay, so let me give you an idea of the proof. So in general, the space of alpha manifolds parameterized by one arbitrary function of one variable. We don't need all of those. Let's just choose n particular ones. So we and then stratify them. So rectify them. Okay, so we have one foliation which is x1 equal to constant, the other foliation which is x2 equal to constant, and so forth. So that will be our coordinates. And so here are, well, actually that's value for our AI. Okay, so we take lambda to be equal to AI, and this has to be foliation. So there's no summation here, right? Because there's just factor, but foliation is given by xi equal to constant. Okay, so now we have this coordinate system. And so we write in it the form omega lambda. So the form necessary therefore becomes such. Okay, so fi is not fixed yet, it's a general function, but the condition that for lambda equal to ai, we get this kind of condition is here. Up to clearly the denominator and so forth. So remember that that's projective freedom. Okay, that's almost we're almost done, but this function is still not determined. So we choose two extra family of foliations. So we choose value an plus 1, and then that has to be foliation. So it has to be something proportional to du, where u is new function. Okay, so we had already coordinates x1 to xn, so u will be, of course, dependent on those, and that's just some factor. And do one more foliation. So we do very similar, fn plus 2 times dv. Okay, so now substituting this in here, we actually find this function fn plus 1, fn plus 2. Okay, so we can express them through partial derivatives of these functions u1 and v1. And now the final trick is that we use projective condition on this lambda parameter, and we put this point to infinity and this point to 0. And then we get the formula which was written in here. Okay, so now that's just parameterization of GL2 structures which possess n plus 2 foliations, right? So it's not yet involutive. So we have to check involutivity condition. So now we take, well, this formula which we obtained, this one, and we check convolutivity conditions. So we write that omega lambda determines the foliation. And this is to say that d omega lambda, which omega lambda is 0. Lambda, however, need not to be constant here. So when we do differentiation, well, so it's for some functions, it's going to be foliation. So if lambda is constant, that's either spectral property, but in general, we cannot expect it. So, well, we're just going to write this system. So here it is. So that's this free form, right? D omega lambda, which omega lambda is this free form. So we collect everything with dx, 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 and then we get this system. Okay. So that well, that's terms which linear in lambda derivatives, and then all other terms are here, and that all other terms, well, that's this long expression. Okay, so this long expression Sij, they will be appear later on. Okay, so that's some amount of PDEs, both for lambda and U and V. So in lambda it's first order, in U and V it's second order. Of course, there's derivative of lambda. There's basically some part of already integrability involved in here, but we really don't want those. So we'd like to eliminate those lambda derivatives. So we would like to see dependence of these equations. It's quite complicated system. Let's denote the left-hand side of the system by Tijk. And we look to all possible syzygies between these differential polynomials in highest derivatives. Okay, and then there is this combination, right, which don't contain derivatives of lambda, but this combination is identically 0, so it's not helpful. But then there's also this combination, which also doesn't contain derivatives of lambda. And turns out that it's precisely equivalent, if we can simplify it, to this system EF, which we had in here. And that's more or less end of the story. So, well, I didn't tell anything about integrability or even compatibility of the system. So what we get?
I'm sorry, I do not understand. This Tijk, yes, how their linear combination can contain derivatives of lambda, because
that's it, right? So that's Tijk. It's not Si, yes, right? And you see this as this lambda I.
Ah, you mean yes, this without S, yes?
Yes, yes. So there's no derivatives of lambda, right? No, the T is there. Well, basically, if I would like to eliminate, I just concentrate on this term, right? Okay. And I would like to see, well, combinations give 0, but actually I see the entire things, right? And that's kind of syzygy, right? I take the combination.
Yes, okay.
Right, and simultaneously with actually removing derivatives of lambda, I also will remove lambda. So I get just PDEs on U and V. And those I get this huge system of PDEs on second order on PDEs on U and V. Okay, that's end of theorem 1. So all involutive are characterized by this big system. So I'm moving towards to say that this is a master equation for all involutive GL2 structures, or alpha integrable GL2 structures. Okay, but theorem 2 will tell us something about this largely overdetermined system. Okay, let's go to theorem 2. So, well, n is level of truncation, right? In principle, it can be infinite, but it's preferable actually to take about something finite dimensional. So it's arbitrary, unrestricted. So the following are conditions. The characteristic variety of the system EF is tangential variety of rational normal curve. Okay, if we take this curve, remember it is curve in projectivized cotangent space. Then we take at every point tangent line. So instead of curve, we get surface. In fact, that's projective picture, right? So we can return to usual affine picture to the entire tangent space, and we have to consider cone over this. It will be 3-dimensional, therefore. Okay, remember this number 3. So second statement. This characteristic variety has as algebraic variety degree 2n minus 4. And so, of course, it's obtained from a rational normal curve as tangential variety, but vice versa, rational normal curve can be recovered as singular locus of this characteristic of this, well, surface in projective space. Third, system EF is an involution, and its general solution depends on 2n minus 1 functions of 3 variables. Okay, this 2n minus 4 is this one, and this 3 was actually dimension of this characteristic variety as affine variety. Okay, so that's basically Cartan-Taylor theorem, right? So, well, no, I don't know. Cartan-Taylor-Serre theorem, that's maybe more correct. So now some counting. Formally, if you look to the system of PDEs AF, it formally consists of n choose 4 E equation and n choose 4 F equation, right? Because every E has 4 indices, I, J, K, L, and they are ordered. There's Q in them, so we have this, right? But they are dependent, algebraically dependent. So only this number 2 n minus 2 choose 2 of them are linearly independent. So basically, we can fix first 2 indices to be, for example, 1, 2, and the other 2 indices let run. It means that they will run from 3 to n. And similarly for F. Okay, so that's degree of overdeterminance. We have that many PDEs of second order on 2 variables. Let's take very particular case. The minimal interesting story is n equal to 4. So for n equal to 4, so this becomes 1 times 2, 2. So we have 2 second order PDEs for 2 functions. It's actually a determined system. And therefore, second order, it depends on 4 functions of 3 variables. So this was derived previously by Bryant when he considered involutive GL2 structures related to exceptional holonomy, but he was doing this through EDS theory. Okay, so here when we do this parameterization, it just becomes Cauchy-Kovalevskaya theory. Okay, so can you please remind me how long is usual lecture? So how much time I have?
Well, you have at least half an hour, maybe more, if you need.
No, I don't need more actually, but I just was thinking whether I have to give some details of the proof of this. So actually, the proof is pretty much applicable, good for this seminar because, like, it's a very good exercise for those who study the book of 3 authors, Vinogradov, Krasильщик, Lechagin. Okay, so let me give some details at least. So let's parameterize rational normal curve. Okay, so as we saw before, it's this parameterization. So Pi is this, and A is this. And how to get tangential variety? Okay, so we have to, well, just take the point and take tangent direction, differentiate this by lambda, and multiply by arbitrary lambda. That's parameter along the line. I call it minus mu, this parameter, okay? So they take this combination. So we have lambda and mu, 2 parameters, that's surface, right, in projective space, in Pn minus 1 at the point. Okay. Now I look to the symbol of this differential equation, and this was quasi-linear equation, so it's very easy. I just see what the top derivatives are, right? There was E and EF equation, right? So and I can take linearization of E in U and linearization of E in V, and very similar for F and realization of F in U and in V, right? So I get a matrix. That's a matrix of the linearization operator. Well, that's actually simple, right? So this is, since this second order, so this is quadratic in P. That's already okay. We know we expect quadrics. So in fact, precise formula is as follows. So for E, well, realization in U is just this. So I take this E, differentiate by, well, top jets, and then I change, well, that's not linearization, that's already a symbol operator. Then I change, well, second derivatives to, well, to Fourier transform to product of differentials to commuting variables. Okay, so in fact, the formula is pretty nice. It is this one. Okay, so I put all of this stuff inside. So so then I would like to see when these metrics actually drop in rank, right? So that's metric 2 times many, and many, that's the number of equations. 2 times n minus 2 choose 2. Okay, and so the first thing I note is the following. So if I take this rational normal curve, okay, this P, and substitute it in here with those values, well, this is just for top corner, but very similar other things, then actually I get identically zero metrics, which means rank is 0. Well, if I take this thing, right, so non-singular part of, well, mu is non-zero, non-singular part of tangent variety to rational normal curve, and substitute here, I get, well, so that's the two columns will be proportional. That means rank 1. Okay, but they will not be 0 if mu is non-zero. And so that shows that, of course, these two gives, well, parameterization of characteristic variety. Well, basically, that's main part and that of singular part. And then it's not difficult actually to argue that that's entire thing. Nothing is lost. So we can go back because the condition is that this matrix 2 times many has, well, rank less than maximal. That's precisely characteristic for the definition of characteristic variety. Well, can be resolved here. Okay, that's about characteristic variety. Then the next thing is involutivity. That's the most complicated thing, right? So the first part I already explained. The second part is just can be extracted from any book on algebraic geometry. That's absolutely standard fact. Okay, so then the third fact is involution of the superdeterminant system, and then this count of function of freedom of solution space. That's Cartan, Kähler, Serre theorem. Okay, so how does involutivity go? Okay, so let me first explain the story for linear. Recall what happens for linear system. We have linear system, right? Then we form symbolic module of this system. So usually we have like in Spencer complexes G1, G2, G3, so forth, but symbolic module is dual. Okay, so now this happens actually at every point. So I would like consider every point. So that's the module over polynomials. Okay, but these polynomials are on cotangent bundle. Okay, polynomials on cotangent bundle, that's ST, where T is tangent bundle, that's symmetric power. I call this ring R calligraphic. Okay, then the equation, so usually, well, that's part of general theory, it's given by some differential operator. And as a standard in geometry of differential equations, if it's case order differential operator, if it's case order equations is E, then this corresponds to bundle morphisms from one jet space to another jet space, where it's just dropped by K in jets. Okay, so we usually like this notation from the book of 3 authors is this. Okay, so now we have the symbolic module ME of the equation, and we construct free resolution. Well, I take minimal, that's not necessary actually, but sometimes, okay, I take, not important, take free resolution. Okay, so in fact, the beginning is just this, I read it from here, okay, or from here if you want. The beginning is just that this is a symbol of this differential operator. And this gives generators for this module. And the next comes syzygies. Well, I compute them and then come syzygies of syzygies and other abstract nonsense. Okay, what I do next, I go to dual complex. But dualization is a bit tricky, right? So you see here the ring, right, R, but I would like to do the dualization over another R, over the field of real numbers. Who likes more complex can do over complex. Okay, so then this dualizes to this. Okay, that's usual symbolic sequence, which appear in Spencer. And then we have, well, the usual bundles associated to Pine New. Okay, so I have these morphisms. Okay, and then this gives us actually compatibility complex. Okay, so usually this helps us, for example, to compute Spencer. So Spencer is based on G, right? So you can think Spencer, for example, is vertical, since this is horizontal. So this G goes to T star tensor G, goes to lambda to T star tensor G, and so forth, right? And you can construct bicomplex, and from this, by browsing through this complex, you can actually, since it's free resolution here, you can compute this homology over here. Okay. But important at this point is the following. So if you take this system, then the compatibility conditions can be written as follows. We take delta, we compose with psi, where psi is differential operator with this system, with this symbol. Okay, and then this has to be zero on equation. That's all compatibility conditions. Okay, that's for linear systems, right? For nonlinear, you do the same story, but just apply linearization. For quasi-linear, it's a kind of simpler because you just froze the lower jets. Okay, so how does it go? And now it goes, well, pretty many symbols. So it's probably will be very difficult to follow. So I compute this. I already told about this linearization. The other linearizations are a bit more complicated, but all of them are explicit. And I do it kind of in the basis of this R2, right? That's polynomial ring R plus another polynomial ring R. So I, well, just note the basis over R calligraphic. Okay, and then there is, of course, well, you remember this matrix, it was 2 times that number. So I also need another basis for to enumerate equations. Okay, and then I encode my symbolic map. And okay, and then I compute this CZG module. Okay, it becomes, it's linear actually. So if I go back to here, so very often this thing is quite a polynomial, but those are just linear, right? So that's all modules over R calligraphic, but these are just linear expressions. And yes, and you see here that those guys, the first which give generators, are quadratic, but all of those are linear in Xi. Okay. You approximate the C complexity, but it's, well, you have to spend some number of minutes really to understand the complexity of this formula. So let me just summarize what we have. So that's our placeholder for 2 functions, U and V, right? So I do everything symbolically. That's our equations, right? And that's where compatibility condition lands. Right, I just take the first part of this long complex because this, I don't actually have any use of the continuation of it. I don't want to talk about it. So I need that this composition is 0. And then it will give me compatibility, and actually it will give me also, well, involutivity. Right, and that's well, okay, but here's one important notion. So I even like just checking this. It's enormously difficult because you see all the stuff. So how to do it? Even it's just polynomials, but it's how to do it. So what we know that if you look carefully to CZGs, they actually are enumerated just by 5 symbols. So you have this I, J, K. And there was 2 symbols, because basically, remember, I fixed 1 and 2 to enumerate equations. So that's actually 5 symbols. So, well, I take 1, 2, I, J, K, but in principle, you can think about 5 arbitrary ordered. And so I have to just check compatibility for 5 indices. Okay, so basically, I take my hierarchy, just take 5th truncation. And then I can do checking. And this is long computation, big computation, but it's finite computation. Okay, that's possible to do. That's how more or less it was done. Okay, so there's some kind of explanation why this 5 is composed 2 plus 3.
Was it done by hand or with some computer support?
Well, it was done by hand and on computer because it's such a big that you actually don't trust your hand computation. But yes, it is was verified on computer as well. But in computers just take some time to encode it, but afterwards, since it's just polynomials, it takes seconds. Okay. So there's actually a bit more abstract formulation how it can be done, right? So I just told you about this stuff, right? But actually, it's possible to construct the entire resolution or compatibility complex if you want. And well, it looks like this. Its dual looks like this, and what is here? It's called, well, it's possible to find even the name for this complex. It's Egon-Northcourt complex. So whenever you get complicated, exact complex, exact sequence over some ring, well, in this case, polynomial ring, then it probably has some name, and that's true. So it's actually take the book by not Boxbaum, not Auslander. What is this book? I forgot. Is it home? Okay, so I forgot the name. Sorry, but yes, just browse and find if you find. Okay, so I don't want to go through this abstract commutative algebra thing. But the thing is that if you carefully look to this, you will find here lambda 3 in this complex. And that's all those IJK which were on previous page. So you kind of make sense of all things which appear in here. If you look to this R2 star tensor R2, that's 2 times 2 matrix. Well, okay, so okay, there are some explanations for this. I don't want to sit here long. Okay, that's theorem 2. So finally, there's theorem 3, which tells that the system EF, which of a determined system, it's actually integrable. Integrable through dispersionless lux, but that's error. Sorry, it's not pair. There's many vector fields. Dispersionless lux representation. Okay. And then we get hierarchy by just letting this n go to infinity because that's embedded sequence. All of them are compatible, and the vector fields are just extended each other, which means distributions are embedded, included into each other, and so forth. Okay, so where is this lux representation? So remember, we go to corresponding space from this space. Well, that's M N U is a solution realized as section of infinite jet bundle, right? But it's diffeomorphic to base. That's why I call it M, but with this letter U, just which remember that it's a solution. And then I take P1 bundle over it, bundles of lambdas, okay? The 1 dimension plus, that's M hat. And on these spaces, where coordinates are x and lambda, here's my vector fields, okay? Again, it seems that there are very many because they're parameterized by 3 indices. Okay, there's also polynomial in lambda, which is very important actually in, yeah, they're quadratic. So which is very important. Oh, no, sorry. No, oh, sorry, I'm not sure they're quadratic. I forgot. To be rechecked. That's not important actually here. But like for Lux pairs, then actually they well, no, they're cubic there, right? So when you do projective leaf, it's quadratic, but then it's a combination of on the basis. Yeah, they're cubic actually, and the same thing here, cubic and lambda. That's correct behavior. So there's this distribution on this one. It has dimension n-2. Right, and well, we can just take those vector fields. We can, well, there's relations and ij can be fixed, right? So it's only L runs from 3 to n. This gives n-2. And well, and that's it. So basically we do check of compatibility, well, for Frobenius for this distribution, and then we get this complicated system which we saw before, right? Sorry, go back, this one, right? And of course, the derivatives of lambda are PSs, and these follows from EF system, from this one. Okay, so that's basically it. Right. So, okay, so we get, well, Lux integrability, and so just to summarize, so all involutive GL2 structures are parameterized by EF system. This involutivity property of GL2 structure is some kind of integrability in Twister sense called alpha integrability, right? And this master equation, this EF equation, the master equation for involutive GL2 structures is integrable in its own. So we can think every particular involutive GL2 structure as a reduction of this EF equation. So the situation is very similar to what we have, for example, in 3-dimension, right? So in 3-dimension, second order equations, or as we generalize with David Calderbank, any system which has quadratic artistic variety in 3D. So it is integrable if and only if it is reduction of a Stein-Wall equation. And so what we did here, it extends this to hierarchies. Okay, so that's the references. Yeah, Eisenbut, I forgot about it. So this book of Eisenbut, it contains a lot of commutative algebra, but it's like 600 or 700 pages. So browse through it is not easy, but yes. So that's our paper with Evgeny Ferapontov, and the details are there, of course, in archive. Okay, so thank you very much for your attention.
Boris, thank you. Questions, remarks?
Есть аналогии.
Well, I have, well, you can consider it either as a question or as a remark. Well, so you call, you say in your terminology, if a system admits a non-isospectral Lux representation, you call it integrable, yes, nevertheless.
Yes.
And then my remark is that there is a lot of examples when system admits a Lux representation without parameter, and then by an artificial trick you can include a sort of fake parameter to this Lux representation, and the parameter will not be the dependence will not be trivial. Yes, but nevertheless the properties of the initial system will not change. So of course it's a matter of terminology, nothing more. But I think that when the Lux pair is non-isospectral, you should be somehow cautious calling it integrable. Боря, включите микрофон.
So you mean there's a lot of examples actually? Are these like Lux pair in vector fields or in differential operators?
Well, I must maybe in operators.
Yes, then it's
Maybe
probably.
yes, you're right.
So because in vector fields, it's kind of just specification. So vanishing, so that this d by d lambda disappears. It's just shows that equation becomes just very special. It's even simpler. It's called linearly degenerate. So in a sense, it means it should be easier to integrate it. And the same like this twistorial approach. So if you go to the twistorial site, that it tells you that it's just easier to integrate it. While for solitonic kind of equations, of course, the situation is different.
Yes, it's different. Yes. Okay, but well, it's it's not an essential remark. Okay, thank you. More remarks and questions. No question, no remark. Okay, Boris, thank you very much.
Okay, thank you very much.
This is our last meeting this year, this horrible year. I wish you a happy new year and Merry Christmas and all the best in the next year. Let's hope that it will be at least a bit better than this one. And our next meeting will take place on February 3. It will be a Wednesday, and as always, 7 p.m. Moscow time. Thank you for attending the seminar, and goodbye and good luck.
С Новым годом, до свидания.
С Новым годом, Боря.
Я хотел спросить насчет вот было IJK, и там были два индекса опущены. Это имеет какое-то отношение к кросс-продукту?
Нет, нет, кросс-продукт это обычно ситуация специфическая для некоторых размерностей, как 3 и 7, да. Здесь никакого ограничения на размерности нет. Здесь просто довольно большая такая симметрия, ну, в плане конечной группы, группа перестановок, да, и поэтому часть из индексов мы просто можем зафиксировать, чтобы не иметь повторяющихся уравнений, чтобы в системе были независимые уравнения. Это просто вот это делается. Да, я нарушаю симметрию по индексам, просто чтобы взять некоторое количество независимых переменных. Независимых уравнений, сори.
Овик?
Да.
No? Okay. More questions? Okay, Боря, thank you. Goodbye. Good luck.
До свидания.